A high-voltage substation is the essential routing hub of the modern electrical grid. It is the physical intersection where massive amounts of power generated at distant plants are received, transformed, and distributed outward to populated load centers. Deep within this node lies a specific convergence point known as the busbar. This is the conductive nerve center, a heavy metal spine where all incoming and outgoing electrical currents physically meet. Designing these convergence points requires solving a harsh engineering tension. A busbar must operate with near-perfect reliability to keep the grid stable, but its construction is bound by strict economic and spatial constraints. That requirement for reliability is tested constantly because these exposed metal structures are inherently vulnerable. They sit outdoors, subjected to extreme environmental stresses, constant lightning strikes, and immense mechanical forces. This bar chart outlines the empirical threat model for busbars. The data shows that 21% of all faults originate from electrical flashovers, while 24% are caused by the failure of switchgear insulation. Zooming in on the specific nature of these events, we see the most dominant failure mode by far. Over 67% of all incidents are single-phase to earth faults, typically caused by a line shorting out to the ground. These massive electrical faults are a statistical inevitability. Because the grid cannot rely on the impossible task of preventing every lightning strike or insulation breakdown, the physical architecture of the substation must be designed to survive them. To engineer that survival, grid operators use a rigorous topological language called the single-line diagram. This diagram uses a standardized alphabet of schematic symbols to map complex systems. Key components include current transformers, capacitive voltage transformers, and isolators, which manage and measure the flow of electricity. Two critical defensive components are the circuit breaker, which physically opens to interrupt dangerous fault currents, and the surge arrestor, which bleeds off extreme voltage spikes before they can damage adjacent equipment. When applied to a real-world, highly complex node, like the 400 kilovolt Bina substation in India, these symbols combine at a massive scale. The overwhelming complexity of this specific 400 kV schematic is the direct result of an evolutionary, step-by-step optimization process. Every breaker and line is placed to defeat the statistical fault threats we just observed. By stripping this dense diagram down to its foundational elements, the underlying mathematical logic of grid survival becomes entirely clear. The evolutionary process starts with the simplest possible topology, the single busbar scheme. Its primary advantages are immediate. It has a low initial cost, it is extremely simple to construct, and it is easy to maintain in locations where temporary network shutdowns are acceptable. Under normal conditions, current flows from generation feeders, merges on the main bus, and exits to the load. But if a localized fault, like a flashover, occurs on this bus, the mechanical reaction is absolute. To clear it, every connected circuit breaker must trip simultaneously. The consequence is severe, a total localized blackout, dropping all connected loads instantly and destabilizing adjacent network nodes relying on that power flow. The single bus topology is economically ideal, but structurally fragile. For critical high-voltage nodes handling vast amounts of regional power, it is entirely insufficient. To prevent total shutdown, we use the single sectionalized bus scheme. The bus divides into section A and B, connected by a tiebreaker. If a fault strikes bus A, the breaker opens. Bus A goes dark, but power through bus B continues unaffected. To push reliability further, engineers developed the duplicate or double main busbar. This features two fully capable parallel main buses. Feeders can be physically switched to connect to either bus using isolator switches. This provides massive operational flexibility. A utility can completely de-energize one bus for maintenance without dropping a single megawatt of active load. During a severe fault on bus A, the system responds rapidly. All incoming and outgoing loads can be routed down through bus B, maintaining uninterrupted power flow across the entire node. However, there is a massive constraint. Achieving this level of redundancy requires doubling the physical footprint of the busbar, heavily increasing raw material costs, and demanding a complex array of interlocking switchgear. While pure duplication successfully buys reliability, it creates an unsustainable geometric scaling cost when applied to massive 400 kV interconnects. This leads to Power Grid's definitive standard for 400 kV networks, the 1.5 breaker scheme. Exactly 3 circuit breakers are installed on a single crosstie to control 2 independent feeder circuits. This specific geometry yields a ratio of 1.5 breakers per feeder. It threads the needle between the low cost of a single bus and the high expense of a fully duplicated bus. In normal operation, both main buses are energized, continuously sharing the electrical load through the closed breaker array. But if a severe fault occurs directly on main bus A, the isolation response is highly contained. Only the top row of breakers opens, datuming the failed bus. The operational triumph is clear. Despite losing an entire main bus, both feeder lines remain fully energized from main bus B. This topology solves the core engineering tension. It achieves maximum operational flexibility and fault tolerance without requiring a costly 2-to-1 ratio of complex switchgear. Moving from theoretical topology to physical construction reveals another layer of complexity. These architectures must be built from hundreds of tons of highly conductive metal. Engineers evaluate copper and aluminum against strict requirements. The metal must have low electrical resistivity, a high softening temperature to survive thermal spikes, and strong mechanical properties to withstand outdoor environments. This comparative data table shows copper holding a distinct technical advantage. Its electrical resistivity is much lower, at 0.0172 ohms, compared to aluminum's 0.0282, and it boasts a higher softening temperature of 200 degrees Celsius. But physical and economic deal breakers dictate the decision. Copper is nearly 9 times as dense as water, and 2.7 times more expensive than aluminum. Suspending hundreds of tons of copper high in the air is structurally punishing and financially prohibitive. Because of this mass-to-cost ratio, aluminum is the industry standard. Power Grid specifically mandates ACSR quad Brasimus or Moose conductors for their massive 400 kV main busbars. Engineering an optimal high-voltage node requires balancing raw physical economics with advanced electrical topology. A brilliant physical topology is useless if a localized fault is not detected and cleared in a matter of milliseconds. This speed is achieved through busbar differential protection, an automated system built on a strict application of Kirchhoff's current law. The logic is elegantly simple. A differential relay continuously monitors the entire array, mathematically summing all incoming current against all outgoing current. Under normal conditions, whatever current enters the node must exit the node. If the sum equals exactly 0, the system knows it is perfectly stable. But if a short to ground occurs inside the bus zone, current violently leaks out. The sum instantly becomes non-zero, and the relay triggers a localized breaker trip within milliseconds. Topological redundancy provides an alternate path, but it is this high-speed mathematical protection that ensures the grid survives long enough to use it. Returning to the EHT Substation schematic, the chaos resolves into structure. If we isolate a single bay, we see a perfect match to our theoretical 1.5 breaker model: 2 main buses, 3 central breakers, and 2 outbound feeders. Moving out toward the transmission lines, we find the specialized protective boundaries, including the specific capacitive voltage transformers measuring the current and surge arresters ready to bleed off external voltage spikes. Remember the opening statistical reality. 67.4% of electrical faults are single-phase to earth shorts. Catastrophic energy discharge is a daily operational certainty for the power grid. Modern civilization runs continuously because the power grid does not attempt the impossible task of preventing all failures. Instead, it expects them. True high-voltage reliability is an architectural achievement built on differential math, aluminum physics, and the indestructible logic of the 1.5 breaker topology.